Hello everyone, welcome to this week's tables. So we'll be starting in a few minutes, waiting for some more people to join. So this week the topic that was covered was word embeddings. So we'll also look at type of code on word embeddings. I mean, if you have any questions, you can discuss those first, and then we'll go to we'll see a code regarding this word embedding. Wait for a few minutes. I guess we can start. So if you have any doubts, first we can discuss those regarding this week or the previous weeks.
Good afternoon, sir.
Hi, good afternoon.
Regarding one of the previous week's question,
Hmm.
uh, assignment 8, question 7.
Yeah, regarding the revenue one.
Yeah,
Hmm.
so it's written the answer is 0. Uh, we will be finding WIXI and then ReLU on that, right?
Right.
So WIXI is coming to be a small value 0.01. So is it like approximated and given the answer as for very small it is?
So is
It
this
is
a
not a negative value to give.
Mhm.
I mean, for 0 it is 0, but uh, we generally calculate max of 0 comma x.
Yes.
So the answer is 0. Can you explain that?
W1 at 0.36. That's W2X2 gives that's 11.1 centimeter. What is that? So if you add these up, what you get? Yeah, if you have to add these up because your value has a connection coming from x1, which has with w1, and it has a connection coming from x2, which has with w2.
Yeah,
So
if we, I mean, first one is 0.36, the other one is
one minus
negative.
1 to 1. Mhm.
Yeah, so
So
since it is negative and
yes, since it is negative, we
minus,
have to add those up. Yeah, w1 x1 plus w2 x2.
okay,
And then you
directly,
have,
yeah, because it is a negative value, we'll just say, okay,
yeah, right.
yeah, thank you.
Yeah, any more questions?
This, when we do SVD,
Mm-hmm.
the
Yeah,
reconstructed dimension,
yes,
we, I mean, when we take those rank 1, rank 2 and all,
yes.
there are fewer dimensionality reduction is there, but the size of the reconstructed uh,
Hmm.
vector is same.
Yeah, the size remains same, but the
So
rank,
is it because just because my rank I'm selecting, but the size is same? Just correct me if I'm wrong. Uh, is it that based on the rank that I'm selecting lesser the rank? That's why it is mm, uh, only the main features are captured, but the size is same.
yes, size remains same because you still have to get the term document matrix letters or any matrix. But the so if you do a full SVD, it will be say
Suppose
suppose
if
it
we
has
have a M cross N matrix and
yes
our U is M cross K and uh, sigma is
A
K
cross
cross
B,
K and
yeah,
V will
Q
be
is
K,
A
yeah.
cross N. Yes. So if you want to calculate A equal to say U into sigma into B, so then you'll
Mm,
have to do a summation of all the K terms. So K
mm,
terms because that is the rank of the matrix, which is given by your sigma.
yeah.
And so now, so even if you say, so when you're doing rank, so let me share, hold on.
Yeah.
So when we have, suppose we are given a matrix A and it is n cross n, So we can do U sigma NP transpose, and this becomes your n cross k. This becomes your k cross k, and this becomes your k cross n. And so we can also write this as summation of that negative sigma
Are
1
you
u1.
using a whiteboard?
Oh, is it not visible?
No, I think I'll
Oh,
have to rejoin
oh,
one. I'll
okay, okay,
rejoin it.
yeah. Yeah, is it visible now?
No, it is still not visible. Yeah,
Oh,
it's
can others?
yeah, yeah. Now I
Oh,
can
okay,
see that. Yeah.
okay.
Visible, sir.
So, okay, thank you. So, okay. So we have this n cross n matrix, and we can write it as a product of three matrices, or we can write it in this way. This plus. So this. So if you look at it, okay. If you observe, so each time you are multiplying this thing,
Mm-hmm.
this sigma item.
Hmm.
So if the rank of, say, if my rank of A is A, so that means my sigma matrix will have K entries here. We'll have sigma 1, sigma 2, and up to sigma 3. And so if so the number of terms that we have here depends on what is the rank that we have. Now, thus, so look at these vectors u1. So u is my
Okay,
m
so
by k.
rank of A, depending on that, this K is depending on that, and I select. But then here if I'm selecting, say, rank one, rank two.
Hmm.
Uh, Sorry, you continue. I'll ask later.
Yeah. So I'm saying that okay, these these sigma values that you have, these are ordered like sigma 1 is greater than sigma 2, and sigma k is the smallest eigenvalue.
Mm.
And so when we are calculating this matrix, so look at this matrix U. So it has m rows and k columns. So that means each column is your so each ui, you can say, is your m dimensional vector. And similarly for V, which is of size n by k, each vi will be your n-dimensional vector. So whenever you are doing ui times vi transpose, you will always get a m cross n matrix. So which is of the same dimension as this. And so that means whenever you do this sum, if whether you take one or two or all of them, you'll always get a m cross n dimensional matrix. So basically, the size of the matrix does not change. Only the only thing that changes is how much information has been used to create it.
Mm.
So if I say I want uh, say I have a rank one approximation of it. So let me say that A1. So A1 is basically your sigma 1 U1 P1 transpose. So now when I want to say that what is the information in A, so let me just check the what is the difference between A and A1. And let me say, so there is something called Frobenius norm. You don't have to worry about it. So
Mm.
this just says that if I, what is the element by element difference that you have. Now, because A was your summation of all of these terms, and A1 is just the single term. So so these things become your difference, right? So what I'm saying is A was summation ui pi transpose sigma I, and A1 is just your sigma 1 U1 U1 transpose. So A minus A1 is basically your summation from I equal to 2 to k, all of the remaining terms, ui, ui transpose. So that means your A1 is not exactly A, it is your size is same, but it is not exactly your A. So to get a good approximation of A, so if you want to say have a rank K approximation, and say suppose you want to make A minus AK equal to 0, that is you want to have the exact metric. So that means you will need to take all of these rank 1 components that you have. So when we say a low rank approximation, it means that we want to have same matrix of the same dimensions, but the information content need not be same as the information that you have in the full matrix. So that is what we mean by low rank approximation or rank
But when
K
I
approximation.
say low rank, I mean when I'm taking only A1, say
Mhm.
rank 1,
Mm.
so when I say that, of course, the less information, but is it that the most important information is getting?
Exactly. So you saw something similar in when you were doing PCA, right?
Yeah.
So for PCA, what did you do? So you were given a matrix A, and then you subtracted the mean from A, and then you computed this covariance matrix A minus this, and you compute the eigenvalues of this matrix, right? So you have
Mhm.
and you compute this type W minimize or sorry maximize over this. And now let me say that A minus mu is your something called A tilde or something. So now I can write the PCA problem as maximize over W, W transpose A tilde W. I can write this like this. I'm just substituting this A tilde. Okay, okay, there is certain mistake. So let me say that I have the covariance matrix here. Covariance matrix computed using this. Say I have some matrix C. So how was C calculated? C was calculated using A tilde transpose A tilde, right? Because that is how you compute the covariance matrix. So when you are computing the eigenvalues of C, you are computing the eigenvalues of A transpose A or A tilde transpose A tilde. Now the eigenvalues of A tilde transpose A tilde is nothing but the singular values of A. So if you remember your SVD constructions, so U is basically your eigenvalues of
A left singular value and
the
right singular value
right A
and
transpose.
sigma. Yeah.
E is basically eigenvalues of A transpose A. So PCA is basically your SVD, you can say, because here these eigenvalues of A transpose becomes your sorry, the eigenvalues of the right singular space becomes your most important or the most principal components. So that means these eigenvalues are the eigenvalues that you get here. These eigenvalues that you get here, these are equal to the singular values of this, the sigma i's that you have. So that means these sigma i's tell us which is the most important component, the second most, third most, and so on. So when you are doing sorry, or whenever doing SVD, so you are just saying that which components you are taking. The first principal component, or equivalently, you can say the most important information, the second most, and so on. So this is same as PCA.
And in our example, when we were doing constructing this uh, co-occurrence matrix,
Mhm.
and if you can go to that distributed represent first time when it was constructed, I don't know, when they say that uh, a corpus was like set of sentences. So
Yes.
when you are calculating, it's like everything is continuous text.
Uh, what do you mean by
If you can open that slide, I
yeah.
can distributed
So
representation first time when it was being explained. So somewhere it was the count was, I mean, without PMI and all, simple count was shown. So I had
uh,
some
are you
mismatch as well.
seeing this?
Yeah. Uh,
Are you seeing my slides?
no slide is not shown. Oh my God, I have to
Okay.
log in again. I mean, you have already opened.
Yeah, I have shared. So
Yes,
can
yes,
anyone
yes.
else? Yeah,
Yeah, we can able to see, sir.
okay,
Yes,
okay,
yes, we
What?
can able.
okay. Can very good.
Uh, okay, I'll
Okay, no
much
issue.
time. I don't know why I have to leave and join every time you open something.
Corpus, no?
Uh,
Corpus human machine interface.
yes, yes.
Okay, I have it written on my notebook. I'll just read it out. So, say for human zero, I got it. So then it is system and user. If you see, it is written the count as 2.
Yes, yes.
So, what I was asking is this set of sentences, is it like they are just joined all the sentences and it's a chunk of
Oh,
text?
so first of all, they will extract the vocabulary. So they will. So there is this process called tokenization. So
Mm,
tokenization basically says, suppose you have this sentence, human machine interface for computer applications. So the
mm,
will try to break it into individual things. So either you can do character level tokenization. So that means human will be broken down into H, U, M, A, N, and so on. Or
mm,
otherwise you can do a word level tokenization. So
mm.
now we'll have tokens like human machine interface for computer applications. So you get
Fine.
around 6 words. And similarly, you do this for, so because we have this corpus of say 4 sentences, you find out each of the, or you tokenize each of these sentences. So obviously, if if a word occurs twice, you do not add it to the set of tokens. So using this, you will have a set of tokens. Now you want to see how many times these words co-occur. So, like you said, for system and
System and
user,
user.
huh. So in the second sentence, if you see user opinion of computer system response time, so there user and
Yeah,
system
if they're
occurs once.
saying that, considering a window of 2,
Hmm.
so how does that come under the window of 2? User opinion of computer system.
Uh, okay, I think it is maybe anything error in this exam.
Yeah, probably. So I was like, is it like, how is it arranged before that? Some kind of, do you, um,
So because in the context, you look at keywords before the word and keywords after the word, and then you construct, or then you see how many times does it occur within this window.
mm,
Because So the thing
I
is,
like getting confused in that. Okay,
yeah.
never mind. And one more question. Many times, what Mitesh sir he corrects the slide and he'll say that okay, TS, please correct this. This is a mistake. This should not be like that. So, can we get the corrected slide when we are getting the?
Oh, regarding so actually I think that these lectures were recorded when they were teaching the course,
Yeah,
and it was around, I don't know
yeah.
when
But
this was
then
recorded.
the slides that we are getting, that I
Mm,
mean that material text which we are getting, because once it's afterwards when we are
mm,
looking up, uh, when it is fresh we can understand. And after
yeah,
later, 1 month down the line, we are
yeah,
looking in, and in those slides, those corrections will not be there, and every correction is not like noted down and all.
yeah.
So,
So
is it possible? Can you check whether they
so
definitely have corrected the slides, right?
so hopefully, their course website is available. I am sharing the link in the chat.
Okay,
So I'm assuming they have uploaded the corrected slides in the website.
okay,
So this is the course website. So if you go below there, can see this, there this lecture PDF.
1 minute.
So if you're able to see the screen, I've opened the course.
I just copied the.
Okay.
Okay, PDF.
Hmm. So if you
Okay, I'll
go
check
down,
it. Okay,
so hopefully they have uploaded these corrected stuff, because
okay, okay,
this is an updated version of the course. Already. Uh,
okay,
so it should be there.
okay. We'll check. Thank you.
So the course actually has some advanced topics like transformers. You can also go through those if you are interested. Oh, okay. If you go down, there are something called tutorials where they have a set of questions. So if you're interested in some examples to work out, you can also go
Mhm.
through those questions.
Okay. Another thing was
Hmm.
in this when uh, this hierarchical softmax was
Hmm.
being taught at that time. Uh, he said something like number of leaf nodes is same as number of nodes, non-leaf nodes. It's not
Okay.
possible. I mean, for a binary tree. 1 minute, I'll just re-log in. Otherwise, if you write something on the whiteboard, I will.
Okay. Yeah, are you able to see?
For a binary tree in hierarchical softmax, now I can see here. Number of leaf nodes is same as number of non-leaf nodes. That's not true.
Can you tell me the slide?
In the slide that hierarchical softmax timestamp 3 minutes 3.46.
Uh,
In the beginning only that I anyways just moved on. I mean,
Okay.
it's not possible like that.
So for some reason, the pages are not getting.
Because that's how they put that number of parameters in that as bag of words. So because
Okay, let me go to this. Give me a few minutes because my page is not loading. So
and also this was actually one of the solutions to one of the solutions
oh,
with skip gram and bag of words. But the question was like, uh, isn't tree building a tree more complex for memory?
so you don't have to create a tree explicitly. I mean, you can just okay. I've not thought about the implementation, but you can just keep caching or not caching. I mean to say that once you have completed the part, you can just keep it. I guess. Uh, I don't think they construct the binary exactly because, yeah, you need the 2 to the n nodes for that. So that is very complicated. Uh, so where do they mention that number of?
Timestamp is 3 minutes 46, 3.46.
Oh, uh, do you have the slide number?
This is hierarchical softmax. This is slide number, I don't know. It must be like week 9, so it might be like
3
lecture
minutes
10.
46. Okay. there exists a unique part and we not very weak now.
So it just says lecture 10, slide number, we don't get it.
Okay. Okay, anyway, I have the PPT open now. Okay. So yeah, I got lost. What was the question? Okay.
Number of leaf nodes is same as number of non-leaf nodes.
Oh, so okay. So why they say this is because you are generating, let us say, you're generating a text. Uh, so suppose uh, because you need to have all of the words that you want to learn on, right? Like uh,
And in that example also we can see that there are 8 nodes, leaf nodes, but the non-leaf are 7. So something I'm missing, not able to understand how.
so let me think about it because I've gone through this part. Give me a few minutes.
Yeah, yeah, sure.
So now we are looking at word generation, right? Right. So suppose my sentence is say uh, the cat plays with a ball. So first of all, my word say I want to come up with the word which, let us say. So I will
Hmm.
start up with something. Say I have da here, and then it should come up with something. Say with. So it has to follow this part. From da, it will go to cat. So then it will go to plays, and then it will come to this. So here you still need to look at all of the words that you have to make the decisions.
Hmm.
So that means you need to have all of the items of the vocabulary that you had initially. So that means you need, so here because you need all of these, the decision comes to all of these leaf nodes. But to come to that, you still have to go through all of the vocabularies that you had, all of the sorry, words in the vocabularies that you have. So that means it must have the size of the nodes. Is that, I don't know if it, so
In that slide, if you see, the size is not same.
Yeah, here the slide is.
But generally, for if you wanted to make a tree with uh, three nodes also,
Mhm.
you have one root and then it will split
Yes.
two.
Two.
So,
Yes.
so the leaf and non-leaf is not same, no? That
Not
was
same.
my question.
Mhm.
It will be always one less.
So actually, if I remember correctly, there is a theorem that says that number of we have n nodes, and you are making a tree with n nodes. The
Yeah, because
last
it
layer
is
has
at the
n by
last.
2 nodes. Ah,
Yeah. So
so
if you
the
are having that
hmm,
this leaf load, all the leaf nodes are my uh, from the vocabulary. All the non-leaf is also from my vocabulary.
yeah, yes, right.
How is, yeah, that is not possible. No? You can see that in this path, one will be less only, even if you when you construct this.
Because we have still not looked at weeks yet. Excuse me.
This simple one only, like if you
Mhm.
construct.
So actually, it should have all of these, right? Because even though in this part you don't have the word with, but for there may be some other part which will have the word with. So suppose I am trying to go to this word fall. So there will be some path. You can have some path like this, say like this. So somewhere the word with will be there. Then it will come to say A, and then it will come to the word fall. So all of the words in the vocabulary must be there in the non-leaf nodes as well.
No, that concept-wise I understood, but the concept of a tree I did not understand. Like it, maybe I'll actually reconstruct. I will construct one and check. With this example
So
only,
you
I'll construct the trick.
so you mean to which
What
part
I was
is
trying to say is like when if you have a binary tree, your will be more than the. I could be wrong. I mean, this is what I knew that.
What do you do? Your time. Oh, okay. So what do you future plans? Oh, tennis. All the best. What's your name?
okay? Try to
Kyle.
work
You're
this
from
out. I don't know.
so we speak Canada.
If it is not clear, you can
What do you
again
speak? English.
discuss it later.
You're
Also,
from
if it's not clear.
Okay,
What's your
yeah,
name?
we can discuss it.
Or if you have any, I mean, I am not getting what where exactly you are fixing question actually.
Yeah. No, this was just like when a statement was made that for a binary tree, the number of leaf nodes is same as number of non-leaf nodes.
Mhm.
So that statement, how is it true?
Oh, uh, so let us take the example of three nodes. So for three nodes, we have something like this,
Yeah,
or let us say we take
you can make a deeper tree.
uh,
You can,
I mix six nodes. Let us so if my number of nodes is even, so then we have three nodes here and we have three nodes here. But here this floor function comes in. Because number of nodes is odd, so we are having this off by one type of error. If you take even number of nodes, you can just construct. So let us say I take four nodes. So one, two, three, four. I have two leaf nodes and I have two non-leaf nodes.
okay, like that.
Mhm.
Okay, okay,
So in your example, you are taking odd number of nodes, so I think that's why you are having this off
yeah,
by
yeah,
one.
okay, okay, yeah. Thank you, sir.
बना दिया अब खा लो बोला ना खा लेना
Some, some
Uh,
noise is
नहीं
coming.
और अभी बनाया पहले से तो खा लो
Somebody is just not muted.
yeah. Yeah. Any more questions?
I found this one of the toughest week.
Oh,
Uh,
okay. So
AI
even
doesn't.
I have not gone, I don't do a lot of this language processing tasks. So I'm not that familiar with this, but uh, yeah.
Like I had asked a question in the group also, difference between negative sampling and uh, contrastive estimation.
Okay.
So I got this response saying that negative sampling is a type of contrastive estimation.
So, so
Uh,
negative sampling is basically you don't want to
there
do
also
the
you're
full.
taking negative, here also you're taking negative.
Uh,
So confusing.
yeah. So most of the techniques, I mean, these are theoretically grounded, but people did that because it works. But even then, so if you read papers, because if you look at deep learning papers, they just say that okay, this works, and there is no explanation why that works. But
I actually, in the beginning of the lecture, sir had given some acknowledgement to some Ali, what is his full name? I was listening to his lecture.
uh,
Godse, Ali Godse.
Ali works okay.
Yeah, so I was not able to understand something, so I went to the original from where it was taken.
Mhm.
And in, I mean, it's just a joke. And in that, some notation kept changing. So somebody was saying in that Ali Gotse's lecture notation, he kept changing. He said, "This is nothing compared to the original paper. I mean, original to understand and comprehend the original paper was very far
Uh,
more difficult." So this is what you're saying with all these different notation. It's still a very easier way. So when you said about reading paper, oh my god, no, first I have to
yeah,
get catch hold of this only.
yeah, reading papers like yeah, if you're not familiar with it, it takes time to go through.
Yeah, I tried to one of the paper. Oh my god, it looked all Greek and Latin. it was like one of the paper was like each in a sentence, each word was like a concept by itself.
Oh, okay. Mhm.
So
So
gave a
because
concept.
these papers are generally written for reviewers, so reviewers are also uh, you know they also work in this domain, so they are more familiar with the terms. But
Yeah,
if you're
there.
not
Yeah,
familiar, then
the
it becomes
moment.
an issue. Mhm.
So me, it was like all every word was a
Mhm.
co-pilot was on finding
Oh,
out. Okay, what is in the exam? How am I going to do? Because everything I've like I so much I'm relying on. Okay, what does this mean? Okay, what does that mean?
mhm. But in exam, exam the question I don't know. The question will not be that, but it's good to know that that is more important.
Yeah, to understand because not everything is like we've not done. I've not done like probability and totally thorough with probability and linear algebra, and so concepts come and then have to look up. So can you say more on between negative sampling and
Yeah, yeah.
contrastive
So
estimation?
yeah. So let me actually I'm going through this. Give me a release. So for this, so the basic concept is same for your negative sampling and contrastive estimation, but the only thing is how do you optimize that? Like for negative sampling, what we do is we want to say that similar words will have high dot product, and you want to minimize the dot product of your or minimize the similarity of the dissimilar words. But for contrastive sampling, so this whole idea of contrastive learning, what they do is they want to say that we want my similar things to have high scores, and I want my dissimilar things to have uh, a lower score, let us say. So in negative sampling, you are doing this. You are maximizing one and maximizing the high scores or similar words and minimizing the dot product of the dissimilar words. But in contrastive learning, what you do is you maximize or you get these scores, and at the same time you say that, okay, I am also pulling these things apart. uh, I want a clear distinction between what are the good words or what are the good pair of words, and what are the bad pair of words. So you can think of contrastive estimation as being an additional step above negative sampling. You get the scores, and after that you try to pull these two pairs of words in different directions.
And
So
getting the score is how are they getting the score?
So you train these matrices. So you concatenate these words. Say, for example, they
Yeah,
show this set on and set of Pakatanga. You get
yeah.
their word embeddings, you concatenate the words, and then you try to generate these words, right? So if I see your set word set, how
Yeah, it
what is
said that you predict the score of the this being correct. How
Mhm.
correct is this? You predict the
Yes,
score.
yeah. So you get some scores, and at the same time, once so the way this system is built will be something like this. Okay, so you have a good pair of words. Say, how should I say? So let us say you have this set on, and you have this pair of words set, and let us say A, B, D, or something. And now I uh, get some score for this. I get some score for this, right? And then on top of this, this will again go to a loss function. So there will be a loss function here. And this loss function will try to maximize the difference between these two scores. So this whole thing will back propagate again. This whole thing will back propagate again. And uh, during that back propagation, these scores will again get updated. So that means the weight
So
matrices that you have
initially
will
you
get
are
updated.
taking some random score.
Initially, let us say with some initial W will get some score, and then when you back propagate, your W will be updated, and once your W's are updated, your scores will be updated accordingly. With the added constraint that these two scores should be very far apart.
Okay.
If any more questions, or you can go through a PyTorch example.
Yeah, you can.
Yes, yeah, so it's my invisible. So I took these from uh, tutorials of PyTorch. So we really see how this word embedding is really. So I'm doing this in Colab. You can also share the link. You can also play with this code. So I'm sharing the link of this Colab here. Uh, So yeah, there's a bunch of stuff we're going to do this. So whenever you're working with PyTorch, these are some standard things that you'll always need. You need torch. You need this thing called NN because if you want to design a neural network, you have to call this NN.module
Can
functions.
you
So,
resend that link?
oh, okay. Did you get it?
No. Okay. Never mind. Oh, yeah, I got it. Thanks.
So yeah. So these are some standard functions in PyTorch that are always required. So this NN will have your so how do you define your neural network? Like so neural networks will have say linear layers, or it will have later on we'll see it will have what they say convolutional layers, or you will have some recurrent neural networks. So all of these things are defined within this NN. So whenever you are designing a neural network, you will have to call NN dot something. So again, you'll need this ReLU activation or some other activation that you might be using, so that will come inside this functional app. And at last, you need to optimize, right? You need to use say SVD, sorry SGD or ADAM for optimizing your network. So we have these library package called Optim. So here is a simple example. We're just saying that I have two words, hello and world, and I say that okay, like my word hello is at index 0 and world is at index 1, and then there is this uh, in NN, torch NN, there is this function called embedding. So that will create your five-dimensional embedding. So you have two words, hello and world. You'll have a five-dimensional embedding for word hello and two-dimensional embedding for word this word, right? And now you want to create this lookup table. Like you give you give your
So phi is the dimensions, and that will be the features of the word, right?
fi-
What all features
five is the
based on that.
dimension.
Yeah.
Yes.
And two is,
Two is you have two words, hello and world.
oh, okay, okay, number of words.
So
Okay, okay. Yeah.
this becomes your vocabulary.
Yeah.
And for each word, you have a five-dimensional
Yeah.
embedding.
Okay.
Right? And then you create this something called lookup tensor. So lookup tensor basically says which index of the word that you are trying to look up. So if I print this lookup tensor, so here they are saying that okay, I want to look up to my word hello. That is, I want to see how my embedding for my word hello looks like. So it looks like something like this. There is this vector. So this has been learned maybe using word to pack. Okay, so they have learned this word called embeddings. Um, they have this function embedding, and if you go there, if you just scroll over this, you can just see how that embedding has been created, how that function has been created. And so now we have these uh, uh, these embedding vectors. So again, why this is important? So earlier, when we we were not looking at these texts, or we have not still looked at images, but we just thought of the input as your vectors, right? You have given a vector x of 3 dimension, and you have some numbers and so on. But for text, you cannot just give the word hello, and because hello is a word of strings, and uh, these deep learning models only work on vectors. So you have to convert your word to a vector, and then you put this input. And so that's why we have this embedding layer. So given any word or given the vocabulary, you create an embedding of each of these words, and then you do your downstream task. So I think this is a simple example. If you are also creating a neural network for some text-based task, you will be using this NN.embedding thing here. And if you want, say, some other embedding technique, let us say if you want to say glove or something, you will pass this vocabulary to, so you can in fact download glove here, or you can download the glove embeddings and then use those to embed your codes. So here they have taken an example of n-gram language modeling. So language modeling basically says that given a set of sentences or given a set of documents, you want to model the uh, the corpus that you have. That is, if I give you a word, I want to know with which probability the next word, or given a word, what is the probability of another word occurring after this. So mathematically, this is just written something like this. So suppose you are given these words, I minus one, I minus two, and so on. Say your context length is uh, n or n plus one, or 10. And what is the I? What is the probability of the ith word being wi? So if you have used ChatGPT, I think most of you have used ChatGPT. You see that the way the words appear is, if it is working slowly, sometimes like if it has a lot of latency, you can see that the word appears one by one. So that is actually language modeling, right? ChatGPT is large language model, LLM. So they generate words in this way. You give your question, and given your question, it tries to generate the next word, and they do this word by word. So that is what is this language modeling example. And this is called n-gram language modeling because you are like using a bunch of words to do that. So let us say your context size is 2, your embedding dimension is 10, and you are given this sentence about some Shakespeare's sonnet. And so now you have to tokenize the input. So tokenizing means you cannot give this whole sentence as you cannot give this sentence as a what you say input. You have to break it down into words. So we'll have this when, we have 40, winter, shall, and also all of these things. And so they define this set of enzymes. So let me read this a little bit here. So here, since we're using a set of 2 words, you see this is how they look like. The n comes 40 when enters 40 shell. So that means it is showing the when 40 winters. So you are given this word and you're looking at the previous 2 words, right? So you are given this word winters and you're looking at the set of keywords. Or you're looking at this word shell and you're looking at the previous two words as context. So context means suppose your machine sees this word for and winters, what should be the next word? So shell should be the next word. So that is what we mean by context. So they create these n-grams here, and then so this set is basically a Python function. It converts your uh, some list into a set. So here we define the neural network that learns these probabilities of or learning the probabilities means you are modeling the language. So you are learning all of these probabilities for all of the words that you have. That means you are modeling the language. So they name it n-gram language module or language modeler. So like I was saying, whenever you are trying to create a network, you have to import from this NN package that you imported beforehand. And there is something called nn.module. This module basically defines how you describe a neural network. So again, you do this initialization, you have these constructors, and then you define what are the layers that you have. So first will be the embedding layer because you will be given a set of words and you have to learn their embeddings first, or you have to get their embeddings first. Followed by this, you will pass your embedding. So now you are in the, once you get the embeddings, you have vectors, and now you are free to use any neural network that you have. So here, so for embeddings, you can see that the input will be vocab size. That is the mod of V that you saw in the slides. And from then, say there are maybe 100 words here. And from 100, you want to go to 10. So if you are doing, say, one hot encoding, right? One hot encoding will just say that whether, so suppose when I look at this word when, so when should, so in the vocabulary, if when appears at location 10, so we will have a 100-dimensional vector. All of those will be 0 and 10 will be your uh, or at the location 10 you have a 1. So that means for each word, for example when, you'll have a 100-dimensional vector. But now I say, okay, I don't want to look at 100-dimensional vectors, I just need to look at a 10-dimensional vector. So that's how you define this. So these embeddings, so the first argument says what is my input dimension, and the second argument says what is my output direction. So that means you are going from 100 to 10. So the second part is now you have vectors, and in the embedding dimension you are also given the context, right? So
So
above
can you
is
explain this 100 to 10 once again?
oh, okay. So suppose you were doing one hot input, right? And
Yeah.
given this test sentence, so suppose there are 100 words in this test sentence, and now when I look at the word when, so you see when here occurs 3 times here. But anyway, so how will I do one hot encoding of the word when? So I'll
Okay.
basically have a 100-dimensional vector, and suppose one occurs at location 0 in this case. So at 0, I'll place a 1 and all of the others will be 0. So
Yeah.
for one word, you need a 100-dimensional embedding. But if I don't want to use the naive one hot encoding, I want to use some advanced encodings. Let us say the embeddings defined by PyTorch. So I just said I want a 10-dimensional representation of my word. So now
Okay.
instead
Some
of
other,
this
not one hot, some other it is using. That's
some
why
other,
that
yeah,
I'm
this
okay, got
this
it.
will be some, yeah.
Okay.
So that's how you describe it in this. Whenever you are creating a network, you describe what is your input dimension and what will be the output dimension. That is what we need to give. And so, like we defined above that, we have a context size of 2. So for each embedding, for each word, you'll also have a context attached to that word. So like you see here, so this is the word, and along with this, you have a context of this also. So that means for this, you have 1, 2, 3, an embedding of 3. When you get the data set, oh sorry, not data set. When I'm getting the input, you have the word as well as the context that came with it. So that is why uh, you are also the first layer of your linear neural network will have embedding dimension times the context size. Hope this is clear. So now from this, I want to go to, let us say, 128 dimension. So there is nothing special about 128. You can just so if you want more result, better results, you can use a higher number than 128. But the challenge is to get good results for lesser number of smaller sizes. And then once you pass your vector through linear one, now at this point you will have a 128 dimensional vector. And now after this, you so what was the task? My task was to model this language, right? So that means you want probabilities for each of these words. So that means you need your output will have size of the vocabulary. So that is what they're doing. After 120, you again go back to the vocabulary size. So is the creation of the network clear? This is a very simple network. Yeah, any questions? Or moving forward?
What is context size here?
The context size is so in the context means that uh, some word you are given some word, what context does it appear? So suppose if I use the word, let us what is it? I have the word bat, right? And if I say the child is playing with the bat, so that bat will mean that yeah, that's a bad example. The child is what? Okay, the bat is used for hitting a ball, right? So that means you are talking about this wooden bat, cricket bat, let us say. And
Mm.
then you have another word, let us say another sentence, the bat is eating a fruit. So now the bat is eating a fruit means that you are referring to the animal that is bat. So depending on the context that you have, the same word can have two meanings, right? So in the first case, the bat and has a context, say plays, ball, and so on. So that you know that okay, we're referring to this bat as the playing bat, wooden bat. But at the second stage, when you have bat eats fruit, so this eats and fruit are context. Using this context, you know that okay, we're referring to the pet that is an animal. So that is what we mean by context.
Yeah, I mean, that I understood, but
Okay.
here, context size, if you are saying that variable as context size, so
Mhm.
you are giving that context size as
Oh, so this is the context size that you have to just be defined here.
context size 2. Okay.
Okay. So once you have created a network, your next step is to define how your data flows through the network. So in PyTorch, there will always be a forward function. So this first thing is an init function that you will always have to give to initialize your network. or construct your network, and then you have to define this forward function which just says how does your data flow through the network. So let us say my input is, we have some inputs. So again, the first step was generating the embeddings, right? So you pass these inputs to these embeddings that you define here, and you get back the set of embeddings. Now, uh, since it is a neural network, you have to introduce nonlinearity, right? So you pass those embeddings through the linear one layer, and then you apply ReLU on top of that. You take this output and you pass it through second linear layer, where you go from 128 to vocabulary size, and you get back this out, and then you do a softmax of that. So here PyTorch uses something called as log softmax for computational regions. This is basically, you can think of as softmax that we have. And then your network outputs these probabilities. So this is the this is a very simple network that you have. So now that you have defined the network, now you want to say what is the loss function that you want. How do you want to train the network? So those are two important things that you have to define. So here they are using something called as negative log likelihood loss. So because they have this set of probabilities that they're outputting for each of the word, and you'll also have ground truth, right? You want to say that okay, this is how my words should look like, the probabilities should look like. So for comparing probabilities, there is something called this negative log likelihood loss. And you created a so this neural networks are created as or defined as classes. So you have to create an object for that. So this line does that, creating an object for the neural network. And since you have to optimize, so let us say we are using SDD here. So we are doing SDD. What are you trying to optimize? You're trying to optimize the parameters of the model. So you have to give what parameters you're trying to optimize. And you're using a learning rate of say 0.001. So now comes training the network. So we want to train this network for 10 epochs. You track the loss because you can make many decisions with loss, and you start. So these n grams have already been prepared here, or otherwise there is something called a data loader. Uh, it's not used here. For data loader, basically batches all of your data into small batches, and then it gives you those batches once you call it. But anyway, we have these n grams. So for each of these n-grams, you want to, so for the above example, like you saw, right, you need to create a lookup to extract the embeddings of each word. So this is what we're doing here, context indices. And then you have to give this call in PyTorch, because if you're doing for multiple batches, say you're doing many batch SGD, it will start adding up all of the gradients that you have, and you don't want them. So it always, so this is the mandatory step that we have to always write 0 0 there. Now you get so you have your inputs, and you pass this input to the machine learning neural network model that you define here, and get out the log probabilities that we have. I don't know if I'm audible or not. So let us continue this and we'll look at the recordings. So, okay, to do gradient descent, you need the gradient. So that is, you need to do back propagation. So that's where we call this dot backward step. And this is your gradient update step, optimizer step. And then you run this for 10 box. And then you want to see the embeddings of the word, say the word beauty. So the embedding for the word beauty will look something like this. So there is also a demonstration for continuous break of words. Uh, so you can just play with it and see if you are able to. I mean, this has already been done here, but you can just create a toy model here and then see how what are the embeddings that you get. Yeah, so I'm still not sure if you are able to listen to what I'm saying. So, how about now? Are you able to see my screen now?
No, I can't. Maybe I don't know about others. I need to
Oh,
rejoin.
so anyway, I think you can. Uh, I because this will be recorded, you can look
Yeah,
it up in the
yeah,
details. So in the end of this, there is a toy example that has been given. Because you know how the continuous backward models look like. So try to create that in the example that has been given and try to get this word embedding. So that will be a good exercise if you're interested in coding this up.
sure.
Okay, so this was, I wanted to show you this. I think next week, what, oh, next week is CNNs. Yeah, so there will be a lot. Yeah, I'll also uh, get some notebooks for CNNs. Folks. There's a lot of those available, and you can look at those. So yeah, this was all I had. So any questions from the coding part or anything else? Okay, thank you.